Hi, it is section 4.4, concavity and curve sketching. In the last section, we studied how to identify local extrema and try to use them for curve sketching. In this section, we'll continue curve sketching, but along with a new concept of concavity. Let's look at this definition. The graph of a differential function is concave up on an open interval if f prime is increasing there, and also it is concave down on an open interval if f prime is decreasing. Okay, here let's look at the figure left hand side. For the figure of y equal x cubed, if you look at the interval less than 0, then the slope, f prime is the slope. The slope is large, and along the curve moving right side, the slope becomes smaller, and then slope becomes 0 here. So if you focus on that side, left side, then over the interval, now the f prime is decreasing, slope is decreasing, so it is concave down. Now on the right side over here, y-axis, the slope is 0, and slope becomes larger, which means that f prime is increasing. So here, and on the right side, is the graph is concave up. But the right side is the graph of y equal x squared. The left hand side is large negative. The slope is large negative and becoming large negative and increasing. So here, increasing continuously, and here now the slope becomes 0. So here left hand side, f prime is increasing, so it's concave up. And also right side, again, the slope is 0 here and becoming larger and larger. So again, concave up. So for the graph of y equal x squared, all the way it is concave up. But for the graph of y equal x cubed, is the left hand side, the concave down, and the right side, the concave up. The concave up is often called just convex. Okay, here, once we assume fx is twice differentiable, then from this definition, once f is twice differentiable, f prime is increasing, means that f prime itself is increasing, so the its derivative, which is now second derivative, is positive. Now, here f prime is decreasing, then here that implies that f double prime is smaller than 0. So here we have the second derivative test for concavity. Now f double prime is positive, then graph of f is concave up, and here if double prime is negative, then graph of f is concave down. From the definition, we can see it quite easily, and by using second derivative, we can test the concavity. Now here, we define and so-called the point of inflection, a point, and x-coordinate is c, and y-coordinate is the function value, c and f of c, the point where and has a tangent line. That means that it's differentiable at the point, and here the concavity changes, then the point is called a point of inflection. And here now, in many points, in many cases, the concavity may change, like this one. Here, concave down, and from here, now concave up like that. Then at the point, the concavity changes. Here, concavity is, the second derivative is negative, now second derivative is positive, so that here the concavity changes. But at the point, there's no tangent line because there's no derivative defined, so that you cannot find the tangent line. So the point is not an inflection point. So these two are required. For f of x is x cubed, as in figure 4.4, 0, 0 is an inflection point. You can easily see that here and that side, and the f prime is decreasing, so you can check it quite easily. Now here f prime is 3 x squared, and now f double prime is 6x. For this one, this is negative when x is negative. It's positive when x is positive. So that at 0 and left-hand side, here, left-hand side of 0, the point, that is concave down, and right side of 0 is concave up. So along the point 0, 0, the concavity changed, and also at 0 the derivative exists. So we can find the tangent line. Of course, over there at 0, the slope is 0, so that the tangent line is the same as y equals 0, horizontal flat line. So here two conditions are satisfied: the tangent line, existence of tangent line, and concavity change. Then we say it is a point of inflection or inflection point. Okay. Now we have a remark here. At a point of inflection, either once it's differentiable, second derivative exists, then second derivative must be 0, or second derivative may not exist. We'll see that. Okay, this f double prime c fails to exist. You should not confuse with that case. Here, at the point, the first derivative doesn't exist. But now, at a inflection point, now either once you know a point is inflection point, then at the point, second derivative is 0. But of course, first derivative is well defined, but second derivative may not exist. We'll see example. Okay, here. Determine the concavity and find the inflection points of the functions. Okay, let's begin with f of x. So here f prime, that is 3x squared minus 6x. And f double prime is 6x minus x. Okay, once it is 0, then we can say that is x equal 1. And along with 1 and left-hand side of 1, the value is negative, and 6x minus x, so it's concave down. And okay, you can easily see this one. Okay, and 6x minus x, that is now less than 0 when x is less than 1, is larger than 0 once x is larger than 1. So at 1, the concavity changed. And here at 1, here f prime is well defined. So it has a tangent line. Has a tangent line and concavity changes so that this point is on inflection point. Okay, here we have graph. And now once x equal 1, then y value is 0. So the 1, 0, that point. And left hand side is concavity down and right side concavity up. And we know that at the point, the slope is well defined, so we can find the tangent line. So it is an inflection point. Now we'll go to g of x, and for g of x, we have such graph, so that apparently now that is a point of inflection because it's concavity down and concavity up, and now slope is well defined, and so that we can find a tangent line. Okay, but now here for that example, g prime equal 5 over 3 x to the 2 over 3, and g double prime is same as 5 over 3 times 2 over 3 times x minus 1 over 3. Now that quantity is negative. Okay, this is positive, and if x is negative, then the third power will be negative, and its reciprocal is also negative. Now once x is positive, then here now that must be positive, so that at 0 and the concavity changes, and also at 0 here g prime at 0 equals 0, so that you can find the tangent line, and at 0 y value is 0, so that the tangent line is y equals 0, the flat horizontal line. Okay, so these two conditions are satisfied, having tangent line and concavity changes, so that the point 0, 0 is on the inflection point, but here at the point the second derivative doesn't exist, and once x equals 0 the value goes to infinity, so that second derivative doesn't exist. But here we have inflection point. Okay, now we'll consider second derivative test for local extrema, and we want to decide for the critical point, and we want to decide whether it is a local maxima or a local minima. So here, part A, f prime at c equals 0, which means that c is a critical point. That means that it is differentiable and the graph is flat at the point, so that your tangent line is flat. So it can be local maximum or local minimum or inflection point. But anyway, here we have f prime is 0, so the momentarily at c the graph is 0. Okay, so I mean the slope is 0, and f double prime is negative. That means that is concave down. Concave down means slope becomes smaller and smaller, so that only the possibility is at a point C is flat, and then here the concavity down means that it's coming up and now go down, so that at the point there is a flat tangent line, and in this case now there's concave down, so that the point must be local maximum. Now the same A is flat at the point, So it's a tangent line as horizontal line, and now second derivative is positive. Then we know that already over there, here second derivative is positive, then it's concave up. Okay, so it's concave up, and then here at the point we have a local minimum, and that is pictorially we can explain in this way. At a point here now the flat, so that but concave up, which means that it's go down and up like that, and concave up at the point, then is the slope is becoming larger around the C, so that the point must be local minimum. So you may exemplify f of x in this way. And for part B, for example, now y equal x squared or fx equal x squared, then from this one, now y prime equal 2x and y double prime is 2. That is at 0, this one, the derivative is 0, at 0, and also second derivative is positive. So y equal x squared as shape, and here we already know that it is given in this way. So at 0, that is local minimum. For this example, it's global minimum, but anyway, local minimum. And for that one, you can use the example, for example, here now y equal minus x squared. Then at 0 is derivative is 0, and then also second derivative out of that one, here y prime is minus 2x, and here again y double prime equal minus 2. So it is a second derivative is negative, and shape of this function is, okay, pictorially, here we have that, and now that way concave down here, that is the local maximum, right? Once it is a critical point and f double prime is 0, then now for local extrema, and it fails to test anyway. Okay, so the function may have local maximum or local minimum or neither. So for example, here now, okay, y equal x cubed, then here now y double prime equal 6x at x equal 0. The second derivative is 0. So once it is 0, then now the point is inflection point, and it's not local maximum nor local minimum, right? But sometimes here, so that sometimes anyway, f double prime is 0, then it's not easy to find the local extrema. Okay. Okay, now we try to sketch the graph of the given function, and we'll try to identify the local extreme points, the inflection point, and concavity. Okay, here we start with f prime, that is 4x cubed and minus 12x squared. And if you set this as 0, then here now, that is, okay, now from this one, 4x squared is common and x minus 3. So we have here, get equal 0, so x equal 0 and x equal 3, we have the critical points. So 0 and 3 are critical points. Okay, now from second derivative, that is 12x squared minus 24x, and that is same as 12x and x minus 2 if it is 0, then we have x equals 0 and x equals 2 here at this point, and the graph has the inflection points, so that we have here now the table. Okay, now f prime is 0 here and here. They are critical points. And then now f double prime is 0 at 0 and at 2. Okay, now, and once you think here now, around 0 and 2 and 3, then we can see the signs of f prime. Okay, now that one is, this is a cubic polynomial, and then now once less than 3, then it's negative, so that your sign of f prime is negative here and negative, and momentarily it becomes 0 but negative, and again at 2 it must be negative, negative, and right side the sign of f prime must be positive. Okay, now for f double prime here at 0, at 2, the f double prime is 0, but the picture of f double prime is given in this way: 0 and 2, 0 and like that. That is what I call f double prime. And x is less than 0, then it's positive, and between 0 and 2 is negative, and again larger than 2 is positive. So we'll say here now, okay, less than 0, f double prime is positive. Okay, now here between 0 and 2 is negative, and larger than 2 is positive, right? Okay, let's try to put positive a little bit better way. Okay, that's the signs of f prime and f double prime. Now to sketch the graph, and we may try to use here the special point and critical point, and here now key points. Okay, now when x equals 0, the f of x is 0, then f of x is 10. When it is 2, so then f of 2, that is same as now, that is 16 minus, and 32 here, that is plus 10. Okay, f of 2, that is now 26 minus 32 minus 6, and f at 3, the value is now 81 minus, that is, okay, 4 times 27 plus 10. That is same as 27, that's 3 times 27 and minus 4 plus 10, which is minus 1. So 10 minus here minus 10 minus okay, that is 27, so that is minus 17. Okay, yeah, minus 27, 10, so the minus 17. Okay, so we'll write down here, that is at 2 the value is minus 6, and here the value is minus 17. So now we'll try to see the behavior of f. Okay, that means here negative means it's going down. F double prime positive means and concave up. So down but concave up. So that it's going down like that. Now this is going down. F prime is negative means going down. But f double prime negative means here concave down. So the down and concave down. So that like that. and here, and f prime is negative means going down, but a positive f double prime means concave up. So exactly around there. Here the same way, down but concave up. Right? Now here, that is positive is going up but concave up. So that is up and concave up like that. Now these are concavity and behavior of f. So that from this one, now you can make the graph very nicely. Here we have, okay, that is x and y coordinates. There's y direction, that is x direction. At 0, the value is 10. Let's put here now, that is 10. So it is passing this one, and x equal 2. Okay, at x equal 2, that is 2. X equal 2, the value is minus x. Okay, that is now minus x. It's passing this point, and at x equal 3, now it's passing minus 17. So we put here now, that is minus 17. Okay. So here, okay, it is going down, okay, around there, and less than 0 is going down and concave way. So it is going down this way. Between 0 and 2 is going down but concave down way. Now between 2 and 3 is going down but concave up way. So that is concave up way, like, okay, like that. And then the right side of 3 up and concave up like that. Right? So that, and around there, the graph must be, let's try to use a red pen. And here, there's go down, and now go down but concave down way, and passing the point. And from the point, and that is now concave up way, and right side of 3 is up and concave up like that. So that is rough sketch of the graph. And we know that at the point, the concavity changed, so that is an inflection point. Here we have again, is concave down and concave up, so that is another the point of inflection. Okay? So we have a summary for stitched for graphing. First, you have to identify the domain, and also if it is symmetric, then you may try to explore symmetry and try to get derivatives, and first derivative and second derivative, and now find critical points. So practically, now domain and symmetry, and start thinking here critical points, and also you have to here find where it is increasing and where it is decreasing, like this one. By checking f prime, you can easily find that. Also, you can find the inflection point and now concavity. Now by using second derivative, you can find the concavity. Once it's positive, then it's concave up. Once it's negative, then it's concave down. So that you can make eventually the behavior of the function. And when you try to make the graph, and you have to start with, for example, plot key points, like here, now the inflection points or critical points, and if possible, you may try to get your intercept. So once it is, for this example, if you try to find intercept, then it's not easy. Okay, right now, equals 0, y equals 0, then you have to solve this quadratic, this fourth order equation, but it's not easy anyway. But once it is easy to find, then try to find such intercept. For y-intercept for this example is given already. Okay, so in the beginning, you plot key points and then sketch the curve with any asymptotes. For this example, there's no asymptotes, so that we didn't put it. But here, once you have any asymptotes found, then you have to use it to get better graph. Okay. Okay, let's go to here this example. Graph the following functions using appropriate method from the graphing procedures, identifying the coordinates of any local extreme points and inflection points. Okay, let's begin with this one. Now, start with the derivative. And here now, y prime equal 3x squared minus 3. So that if you put this is equal, then now x squared is 1, so the x is now plus minus 1. So plus minus 1, and you have critical points. And how about y double prime? That is here now 6x. So if it is 0, then now x equals 0. At 0, you will have inflection points. So you can make a table as in the previous example. Now, what you have considered minus 1 and 0 and 1. Okay, so here we have, that is now x values is minus 1, 0, and 1. Okay. Now, f prime, okay, here, and that is now, okay, the graph of f prime is given in this way. Between minus n and 1 is given in this way. That is y equal f prime. So that is minus 1 and 1. If it is less than minus 1, is positive. Between 1 and minus 1 and 1 is negative, and larger than 1 is positive. So that here, this is positive, here negative, negative, and then positive. Okay. Of course, over there, now at minus 1, at 1, the value is 0. Now, how about f double prime? Once x equals 0, then f double prime is 0. But left-hand side, the value is negative. So here you have a negative, and right side, the value is positive. Of course, if you try to put over there, then you can see here now, like that. Now, you may try to find the f value. Then at minus 1, here, minus 1 plus 3, so that at minus 1, now the value is 6 minus 1, so that the f value is 5. So minus 1 and 5 is a critical point. And at 0, and that is 3, and now at 1, and 1 minus 3 plus 3, so that the value is 1. Okay. Now here, the behavior of f. Okay, behavior of f, that is less than minus 1. It is increasing, but concave down, so that it is increasing concave down, decreasing concave down, and decreasing concave up, and increasing concave up. Right? Okay, along with that information, we can now make the picture for the graph. Now at minus 1 here, that is minus 1, the value is 5. Okay, that is now 5, and that's minus 1. it's 0, the value is 3. Okay, that is 3. So passing this point and passing that point, and then at 1, the value is 1. At 1, now the value is 1 here, 1. So it is passing this 3 points. Left over -1, it is increasing but concave down, so it is increasing concave down. And between -1 and 1, -1 and 0, down and concave down. And between 0 and 1 is down but concave up way. So the down but concave up. Here, right side of 1, up and concave up, like that. Here, so of course here, the point at 0, 0,3 is inflection point, and this is a local maxima, and that is a local minimum, right? That is the graph of the function. For this one, also, you can do it quite easily. Now, the same, yeah, but now domain is given 0 to 2 pi. Okay. So anyway, now y prime equals same as 3 square root of 3 and minus 10 sine x. If it is equal, okay, this is 5, okay, 5. So that in this case, sine x must be same as now 5 square root of 3 over 10, which is same as square root of 3 over 2. Okay, sine x is given in this way, so you can easily see that here, okay, in the picture. Sine is a vertical component, so that along with the circle of radius 1, now the value over there, so height is now square root over 3, so that angle and that angle. So we have x squared, that is pi over 3, right? Okay. Now pi over 3, and this one is 2 pi over 3. Okay. So we have 2 points, and where the derivative is 0. Okay. Now y double prime, if you are making one more time of derivative, then that is same as now minus 10 cosine x. Once it is 0, that means that here, okay, that means that cosine x is 0, which means that x is now, what is that, pi over 2, and then 3 pi over 2. Cosine is here the horizontal component, and 0 means pi over 2 and 3 pi over 2. Okay, so this will be inflection points, and you can make again now this table, and then you can get the graph. Okay, let's do that here. Okay, there are basically 4 points here. In the beginning, we start with now pi over 3. Okay, x value. Okay, let's try to put x far away from pi over 3. X values. Okay, x values are, the next one is now pi over 2, and then now 2 pi over 3, and 3 pi over 2. Okay. Now, along with that, here f prime is 0 here, here, and here. And then now f prime is now given in this way, so that, for example, now pi over 2, then the value is now 1, so that this is negative, right? So that around there, this is negative, and around there must be positive. You can easily see that. Now for double prime, here 0 happen pi over 2, and now 3 pi over 2, that is 0. And we know that, okay, and once you are choosing pi over 3, then this is positive and along with the negative, so that here left hand side is negative. And if you are choosing here, for example, pi, then cosine pi is -1, and this is positive, so that here we have a positive, and of course over there, just a moment, that one is positive here also, between over there, and the right side also the positive, okay, because it's only 0 here and here for f prime and other area positive. And now we know that, and f double prime is 0 here and here, and between them is positive, earlier negative, and later also negative. So now behavior of f, or you can find f value, but behavior f is given in this way, is increasing, but concave down A. So here around is increasing. Now, okay, now between over there it is decreasing, but concave down A, and between over there is again decreasing, but concave up A, and it's start increasing and concave up. Now and later is increasing but concave down, like that. So that is the behavior of the function. And also you can find f value and try to give the key points, and along with the key points, and you can finish the graph as in this example. You can do it here now, because of the value, it's not simple to make it. Okay, you can do it yourself. But for many functions, the graph can be sketched without computing the second derivative. Sometimes it's quite simple, and so that you don't have to use the second derivative. Okay, for example, for this one, okay, it is symmetric basically, and then now the domain is now 3 minus x squared must be positive, which means that x squared is bounded by 3, so that eventually the domain is the same as minus square root of 3 and larger than that and smaller than square root of 3. That's the domain. Now for that one, now here y prime equal, now function of, okay, logarithm of fx is, now the derivative is f prime over f. So that is a minus 2x divided by 3 minus x squared. Now in the domain, the value is positive, bottom, but over there, now here, if it is 0, then x equals 0, we know that. But anyway, and left hand side, that is positive, and right side with 0, that is negative. That means that here, left hand side is increasing, right side is decreasing. So here, once it's 0, then the value is logarithm 3, so that you can make it in this way. Here now 0, then that is natural logarithm of 3. Now the domain is basically here. There's minus square root of 3. That is square root of 3. And you can see it easily. Now once x is less than 0, and at 0 it must be flat anyway. This is critical point. And then if x is less than 0, then that must be positive, so that it's increasing. And now x is positive, then it is negative, it's decreasing. Also, once, for example, now it's decreasing, but as x moves along the x-axis, then bottom is becoming 0. It's smaller, but the top is becoming larger. That means that this one is also slope is decreasing, which means that, so here now, if x is larger than 0, then y prime is less than 0. However, as x approaches here now square root of 3, we can see that y prime itself is now decreasing, right? So that eventually there is concave down and concave down way, and of course x is approaching minus, okay, in square root of 3, then the value will go to minus infinity. The other way, direction, the other side is symmetric, so it's go down and like that. So that is graph of that function. Of course, you can find here this intercept. In fact, that is, okay, 3 minus x squared equals 1, then y value must be 0. So that is the same as now x squared plus minus square root of 2. So that this point is square root of 2, and that point is minus square root of 2. Okay? That one is also quite easily you can make it. When x equals 1 and minus 1, you have a vertical asymptotes. And also once x, okay, from this one, now x is now plus minus 1, then you have a vertical asymptotes. And x approaches plus minus infinity, then we know that here the y is approaching 0. So that here we have now the horizontal asymptote, that is y equals 0. Right? We know that. Okay. Now for that one, start with y prime, that is now x squared minus 1 and squared by using quotient rule, bottom squared, and now x derivative is 1 and x squared minus 1 minus, and x times now bottom squared, which is 2x. So that is same as, okay, along with here negative, there's x squared minus 2x squared, which is minus x squared. So the x squared minus 1 becomes 1, and x squared minus 1 and squared. So here, and on the domain, y prime is always negative. And we can see, we can make a picture quite easily here now. Okay, here we have, once x equals 0, then y equals 0. So it's passing this point. And once x equals 1 and minus 1, then we have asymptotes. And function is all the way down locally. So minus 1 to 1, also it is down. Now, for that one, now, for example, x is approaching to minus 1, so the minus 1, but from right side, so the f is approach that direction. Then here for that one, now x squared is less than 1, so that y value is now approaching by the 0. Okay, bottom is 0, but less than 0, so that 0 minus, and top one is now minus 1, so that it will become infinity. So here, the value will become infinity. Now, once, for example, x is approaching here, now minus 1 minus, then y is approaching, and once x is approaching from left hand side, then x squared will be larger than 1, but it's approaching 1, so that y will approach here, bottom is 0 plus, and top is the same way, minus 1, so that it will go to minus infinity. So we know that this side, the value is now infinity, and passing that point, and here it is going down. 0 is only the point, the x-intercept. Now, when x is approaching that side, then it will go to minus infinity. But we know that the horizontal asymptote is 0, and except here now 0, there's no other x-intercept, so that here it is along the bottom, below the x-axis, and here we have go down in this way. Also the same way, if you are trying to make x approaches from 1 here positive, then the bottom is positive but approaching 0, and top is positive, so that eventually it will go to infinity. But now is horizontal asymptote is 0, y equals 0, so that never cross x-axis, and then go down and become smaller and smaller and smaller. We can see over there that x equals 0 is only x-intercept. And so we have here already, so that there's no other point passing x-axis. Okay? So that is a rough picture of the function. Okay, this is end of the section. Thank you.